Hallo, it's dumplet here. Here's an item on number theory. M and n are positive integers satisfying m squared plus m is equal to 4n squared plus 5n plus 3. Find all possible ordered pairs m, n. Again, credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Now let's try to focus on the given equation. Now there's a lot of ways to solve like these diophantine equations, but let's try to focus on the fact that we have two variables, m and n, and they're both quadratic. Now there might be a lot of ways to do this. Like one might think, oh, maybe this is going to be like something of the form of the Pell's equation. Or maybe it's going to somehow result in a difference of two squares, and we might be able to factor, and that kind of concerns with perfect squares. So, well, in my case, whenever there is a quadratic diophantine equation, I tend to want to complete the square. Now, well, I realized that this part, 4n squared plus 5n plus 3, that's kind of a little bit more difficult to complete the square, just because of the coefficients 4 and 5 on the end, not really friendly. So I decided to focus on the m squared plus m. Now how do I do this? So I'm going to multiply both sides by 4 first. So I'm going to multiply both sides by 4m squared plus 4m. That's going to equal to 16n squared plus 20n plus 12. And then, well, I want to complete this square, so I'm going to do the plus 1. So 4m squared plus 4m plus 1. And I added 1 here again on the right side, so it's going to be plus 13 in short. And then, well, I have successfully completed my square here. This is equal to 2m plus 1 quantity squared. And there I started my analysis on this, because the right-hand side must be a perfect square. Now, it's a very standard technique in solving quadratic diophantine equations that we might be able to sandwich an expression between two perfect squares. For example, this one, the 16n squared plus 20n plus 13. Well, we know it must be a perfect square because the left-hand side is 2m plus 1 quantity squared. So typically, we might want to find maybe this thing is going to be between two consecutive perfect squares for a sufficiently large value of n. And I just started with like some analysis, like this is approximately 4n plus square root of 5 quantity squared, because this will be the result. And then I decided to look on 4n plus 2 quantity squared and then 4n plus 3 quantity squared. Now, why these two specifically? Because square root of 5, it's between 2 and 3. Well, we're talking about integers, so, well, I have to use integers for this. And then I just try to compare 2m plus 1 quantity squared with these two expressions. And I actually found something very interesting with the 2m plus 1 quantity squared and these two. Oh, sorry, not between 16n squared plus 20n plus 13 and these two, sorry. So I have these two perfect squares, and I did some analysis on these two because, well, I tried to sandwich this expression, the 16n squared plus 20n plus 13, between two perfect squares, and I found something interesting. So the first one, if I want to solve for n in the first one, I'm just going to get something like 4n. It's going to be 4n plus 9. That's going to be greater than 0. Well, that's obviously true for all positive integers n, because, well, the left side is always positive. So, all right, my 16n squared plus 20n plus 13, that's always greater than 4n plus 2. Now, for this one, for the second one, it's kind of interesting as well. If I solve for n in this part, I will get 4n is greater than 4, which is going to give me that for all n greater than 1, it's going to be true. All right, that's something interesting, because if it's true, if this is true, like I can sandwich 16n squared plus 20n plus 13 between two perfect squares, 4n plus 2 quantity squared and 4n plus 3 quantity squared, and this is true for all n greater than 1, well, I'm very sure that if n is greater than 1, then I don't have any solutions. And therefore, if there must be a solution, it can only happen at n equals 1. Just because I can sandwich two perfect squares, sorry, I can sandwich this expression, the red expression, between two perfect squares. So I know n must be equal to 1, and that's the only possible solution. So I'm going to go back to my equation over here. All I have to do is substitute n equals 1, and I have to solve for m. Now if I solve for m, so m squared plus m, now if I substitute n equals 1, this is going to be equal to, if I substitute n equals 1, it's going to be equal to 4 plus 5 plus 3. That's simply equal to 12. And then simple algebra over here, I'm going to get that m squared plus m minus 12 equals 0. Simple factoring, m plus 4 times n minus 3 is equal to 0. I'm going to get two roots, m equals negative 4 and m equals 3. But obviously, I want m to be a positive integer, and therefore, I'll have m equals 3. Now, since if n equals 1, m is equal to 3, I would have the ordered pair that's satisfied, which is going to be 3, 1. And this will be my final answer, and it's the only ordered pair that satisfies the above diophantine equation. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!